24.1 Electric Potential and Potential Difference. In this session, we will explore several key topics related to electric potential. We begin by discussing the conservative nature of electric forces, which allows us to define the electric potential energy of a system. From there, we will provide a formal definition of electric potential, denoted by the symbol V, and distinguish it from potential difference, often called voltage. We will also introduce the volt as the standard unit of measurement and discuss the electron volt, a specific unit of energy frequently used in atomic and nuclear physics. By the end of this lecture, you should understand how these concepts allow us to describe the behavior of charges in an electric field without relying solely on vector quantities. When we place a charge, labeled Q, into an electric field E, the field exerts an electric force on it. We define this force as the product of the charge and the electric field vector. A critical characteristic of this electric force is that it is conservative. This means the work done by the force on a charge moving between 2 points depends only on the starting and ending positions, not the specific path taken. This is very similar to how the gravitational force operates between objects. To analyze these interactions, we treat the charge and the electric field together as a single system. If the charge is free to move, the field does work on it, and we consider this work to be internal to our defined system. To quantify the work and energy in this system, we look at an infinitesimal displacement vector, ds. The internal work done by the electric field is the dot product of the electric force, and this displacement, which simplifies to the charge Q times the dot product of the electric field, E and ds. Because the force is conservative, this internal work is equal to the negative change in the system's electric potential energy, du. For a charge moving from point A to point B, we calculate the total change in electric potential energy by integrating this expression along the path. Because the integral is path-independent, the energy change is determined solely by the field configuration at the start and end points. We define electric potential, V, as the electric potential energy per unit charge. Mathematically, V equals the potential energy, U, divided by the charge, Q. It is important to remember that electric potential is a scalar quantity, meaning it has magnitude but no direction. While potential energy is a characteristic of the entire charge field system, requiring both the field and a charge to exist, the electric potential itself is a characteristic of the field only. It depends strictly on the source charge distribution and has a specific value at every point in space, regardless of whether a second test charge is actually present at that location. In physics, we find that only differences in electric potential are physically meaningful. We define the potential difference, delta, V, as the change in electric potential energy divided by the charge. This is equivalent to the negative line integral of the electric field from point A to point B. Because we only care about the difference, we can choose a convenient reference point where we set the potential, V, to 0. If an external agent, like a battery or a person, moves a charge through this field at a constant velocity, the work done by that agent is equal to the change in potential energy, which is the charge multiplied by the potential difference. This diagram helps us visualize two arbitrary points, A and B, within an electric field. The potential difference between these 2 points exists solely because of the source charges that created the field in the first place. It is a property of the spatial coordinates themselves. However, to talk about electric force, or electric potential energy, we must introduce at least one more charge into the environment. This reinforces the distinction that the field creates the potential, but the interaction between a charge and that field creates the potential energy and the resulting force. The SI unit for both electric potential and potential difference is the volt, abbreviated as V. 1 volt is defined as 1 joule of energy per coulomb of charge. Because potential difference is calculated by integrating the electric field over a distance, we can also express the units of the electric field in terms of volts. While we previously used newtons per coulomb, it is often more practical to use volts per meter. This gives us a new way to interpret the electric field. It represents the rate at which the electric potential changes with respect to position in space. While the volt measures potential, the electron volt, or EV, is a unit of energy. 1 electron volt is the amount of energy a charge field system gains or loses when a single elementary charge, such as an electron, moves through a potential difference of exactly 1 volt. Numerically, 1 electron volt is equal to approximately 1.602 times 10 to the negative 19 joules. This unit is incredibly useful in atomic and nuclear physics because joules are often too large for such small scales. For example, in a dental X-ray machine, electrons are accelerated to energies of about 67 kilo-electron volts before they strike their target. Let us look at a uniform electric field where the field lines are straight, parallel, and directed downward along the negative y-axis. If we move a displacement d from point A to point B parallel to these field lines, the potential difference is simply the negative of the field strength times the distance, or negative ed. The negative sign is crucial. It tells us that electric field lines always point toward regions of lower electric potential. Consequently, when a positive charge moves in the direction of the field lines, the electric potential energy of the charge field system decreases, much like an object losing potential energy as it falls toward the ground. We can better understand these concepts by using a gravitational analogy. On the left, we see a positive charge, Q, in a uniform electric field, E. Moving from point A to point B in the direction of the field decreases the electric potential energy. On the right, we see a mass, M, in a uniform gravitational field, G. Moving the mass from A to B in the direction of the gravity vector decreases the gravitational potential energy. In both systems, moving down the field lines results in a loss of potential energy for the system, which is typically converted into kinetic energy if the object or charge is released. To summarize the main points of this lecture, first, electric potential is a scalar property of the field itself, defined as the potential energy per unit charge. Second, the potential difference between 2 points is calculated as the negative line integral of the electric field along the path between them. Third, a key rule of thumb is that electric field lines always point toward regions of lower electric potential. Finally, remember the units. The volt is the standard SI unit for potential, while the electron volt is a specialized unit used to measure energy at the atomic scale. To wrap up, consider these review questions to test your understanding. First, if a positive charge moves in the direction of an electric field, does the potential energy of the system increase or decrease? How would your answer change if the charge were negative? Second, can you explain the physical distinction between electric potential and electric potential energy? Specifically, think about which of these two quantities depends on the value of the test charge Q, and which one is an inherent property of the field itself. Reflecting on these will help solidify the relationship between field, potential, and energy.